Welcome back to your machine learning A to Z course. Super excited to have you back on board. And today we're kicking off the support vector regression intuition. Super pumped about these tutorials. Got some very exciting slides coming up for you. So what is support vector regression? Well, support vector regression was invented back in the 90s by Vladimir Vapnik and his colleagues who were working at the Bell Labs. At the time that was the AT&T Bell Labs. Now they're Nokia Bell Labs. And a lot of support vector machine and support vector regression are discussed in Vladimir Vapnik's book, The Nature of Statistical Learning, 1992. In this course, we will be covering both support vector machine in the part of the course to do with classification and support vector regression. We'll be talking about it here. And in addition to that, we'll also be talking about kernel support vector machine and kernel support vector regression and the kernel trick and many other things like that. So there's a lot of exciting tutorials on these topics. But for now, we're just going to limit ourselves to support vector regression, specifically linear support vector regression. So here we go. Here we've got two plots, and we need that in order to compare SVR to the simple linear regression. That will really help us understand things. So here on the left, we've got some random plots, random dots. I'm going to copy them over to the right, so we know that these are identical. There's no tricks involved. There's an absolutely identical. This is an absolutely identical set of data. And let's start with the one on the left. We're going to apply a simple linear regression. We've already discussed what it's like, but let's quickly refresh. So basically, we're going to have this line go through the data. And how is this line derived? Well, a method called the ordinary least squares method will be applied. To find this line, basically, we want to minimize the distance between the this value y, the actual value in the data, and y hat, basically what it would have been on a trend line. We take the difference here or difference here, we square it, and we want to minimize that. That's ordinary least squares method. Essentially what we're doing is minimizing the error. We want to have a line with the minimum error possible. So that's the intuition behind a simple linear regression, something we already talked about. Now, how does the support vector regression work? Well, let's have a look on the right. With SVR, instead of a simple line, you'll see a tube. And here you have the regression line in the middle, but then there's this tube around. And what does this tube do? Well, this tube has a width of epsilon, and the width is measured vertically. It's important along this axis, not perpendicular to the tube, but vertically. And this tube itself is called the epsilon-insensitive tube. And what does that mean? Well, that means that any points in our dataset that fall inside the tube, they will be disregarding the error. So basically, this tube, think of it as a margin of error that we are allowing our model to have and not care about any error inside here. So any discrepancy between, or any like distance between this point over here and the line, as in like, for instance, here we could see, let's look at which point is that? That's 1, 2, 3. This third point, you can see the line is even different, right? The results can be different and probably will be different. So this third point here, there's a distance between the line here, and we care about this error. Here, we don't care about this error because it falls within this epsilon-insensitive tube. So we're disregarding any kind of errors in here. And that's kind of the key behind support vector regression. It gives a little bit of movement or a little bit of buffer to our model. And at the same time, we have points that are outside the epsilon-insensitive tube. There they are. And for them, we do care about the error. And here it will be measured as the distance between the point and the tube itself. So not the trend line, but the tube itself. These distances have names. They're either xi star if the point is below the tube, or xi if the point is above the tube. And they're called, so these values xi are called slack variables. So it's either xi star if it's below, xi photo star if it's above. And we do care about the error, so we care about these distances. And the way we care about it, so we're going to try to avoid formulas. I will give additional reading, something you can look into further down at the end of this tutorial. But just for For completeness sake, here is the formula. So in the case of OLS, it was a simple ordinary least squared like that. Here it's a bit more complex. We're not going to talk about this part over here, but what we're focusing on is this, and we can see that we're minimizing. We want these distances, the sum of these distances, to be minimal. Once again, there'll be additional reading at the end if you'd like to go into it, but effectively these points, the ones that are outside our tube, are dictating what the tube will look like, how the tube will be positioned. So the error within the tube is completely disregarded. We don't care about the error, unlike in the ordinary squared. So we're giving some kind of buffer of flexibility to our tube, or like allowing it to accounting for some kind of error that we might expect in the data. It's normal sometimes for there to be error, but these ones, they are important to us. And also, one final thing, why is this method called support vector regression? Well, because effectively these points, all of these points outside, any point actually, any point on this plot is a vector, right? Can be represented as a vector in this two-dimensional space, or a multi-dimensional space if you have more features. So in this case, it can be represented by a two-dimensional vector. So they are all, these points are vectors, but the ones that we've highlighted in red, the ones outside the tube, they're the support vectors because they are dictating how this tube is created. So basically they're supporting the structure or formation of this tube, and that's why they're called support vectors, and that's why this is a support vector regression. And so there we go. That's what it's all about. That's just important to remember the epsilon-insensitive tube, and that support vector regression just cares about the errors of anything that's lying outside this tube. And to finish off, as promised, here's the additional reading. So if you'd like to learn a bit more, have a look at Chapter 4, Support Vector Regression, in a book called Efficient Learning Machines, Theories, Concepts, and Applications for Engineers and System Design by Marietta Wad and Rahul Khanna. And here's a link here where it's aggregated on this portal for published work. Something you'll note that it might be a little bit confusing. Here they say these are potential support vectors. They are referring only to the ones close. I've had a look at different literature, and the literature I prefer is the one that says, in this respect, is the one that says that the support vectors are the ones that are outside, and they are outside basically any point outside the tube is a support vector. So that's how we discussed it inside this tutorial, but have a look at this different nomenclature. Maybe that'll be a good perspective to have a different view. But overall, the first couple of paragraphs describing the whole problem, they're very well written. I liked how they were written, and I think it can be a valuable addition if you're looking for additional reading. So there we go. That's support vector regression. Hope you enjoyed this tutorial, and I look forward to seeing you next time. Until then, happy analyzing.